In this video, we're going to talk about how we estimate parameters and this idea of a sampling distribution. It can be a little bit complicated and take a little while to understand what's going on because a lot of the terminology can be confusing and that words sound very similar but mean slightly different things. So I'm going to talk through it fairly slowly. Feel free to watch at double speed or just read through the explanation in the notes if you're feeling quite confident with this material. So I have an applet here, which I find very handy for demonstrating things. I notice that they've got a note on the side saying that one of the measurements is not calculating correctly, and I have occasionally noticed that some of the other numbers coming up may not be exactly correct, unfortunately. But the applet itself, we mostly want to look at the pictures, so we're still going to do it. Actually, we won't need this bottom one. We're just going to stop here. So we have a parent population, and this is representing something which exists, which we want to find out about, but we don't actually know what it is in most situations. It has a mean of 16. So let's assume that this represents the time taken to get across campus, and the average time is 16 minutes, but it can go anywhere from about very quick to, say, half an hour. It's not a perfect representation, of course. A normal distribution can go negative, but this is a good approximation, perhaps, of what we might find with our data. So what we're going to look at is what would happen if we were taking repeated samples from this parent population. And the reason that we imagine a situation where we do know everything and take repeated samples is because then we can see what would happen. So whereas in reality, we only take the one sample, usually. It's possible we might replicate our experiment, but we take one sample and then we use that one sample to make inferences about our population. So we have a parent population and we're going to take a sample. So we go onto campus, we grab 5 people and we ask them very nicely to get across campus and we time them. So let's draw our sample. So each person, well, they've got fairly similar times actually, and we've got an average. And this is what might happen in an actual study. We only have this information here, our sample data and the mean or the average from our sample data. And what we want to know is how good is this estimate from our sample for the parent population, except we don't know what the parent population looks like. And the way we sort of calculate confidence intervals and make estimates and comparisons is by working out what this shape would look like if we could repeat the sampling over and over and over again. So let's take another sample, and it's slightly different. Every time we take a sample, we'll get a slightly different sample mean. We can take another one and another one. And you can see that this process is quite slow. So we're taking samples of 5 people, that's the n equals 5 here and the n equals 5 here. These numbers here represent how many times we repeat our experiment or trial. It's not truly an experiment unless you impose a condition, or we could just call it a study. How many repetitions? And you'll notice here that the mean is not calculating accurately at all because it's got 0 minutes. So everyone's teleporting from one side of campus to the other. So we won't pay too much attention to these numbers. So let's repeat the study another 5 times. We've repeated the study 100 times now. And you hopefully are getting the idea that this distribution of means is starting to look a bit normal. It's not as spread out as the original distribution, and that's because we're taking samples of 5 and we're calculating the average from each person. So if we take larger and larger samples, our estimates of the mean will become more and more accurate, and this distribution of means will become closer and closer together. So let's take 10,000, 100,000. Okay, this is pretty stable now. This is what our distribution of means look like if we're sampling from this distribution with a sample size of 5. So this is our sampling distribution for the mean in this situation. 5 is a very small sample size, and you'll notice that this distribution is actually not a lot more accurate, if we're estimating the mean, than just the original parent population. So it's not that much better to measure 5 people than it might be to measure, say, 1 person. There is an improvement, but we could do better if we had a bigger sample size. So if we take a bigger sample size, we would expect the estimate of the mean to be more consistent between each sample. And that means that the distribution of means would look a little bit closer in. It wouldn't be quite so spread out because it would be more accurate. So if I bump this up to 20, I better clear that. I don't know if it's storing any data in the background. And take 100,000 samples straight away, you can see that, yes, it's a little bit tighter, closer in. It's getting more accurate. Also, the numbers appear to be correct on the left-hand side now. We've got a mean of 16. Let's go to a sample size of 25 and do it again. And it looks fairly similar. It's a shame we can't superimpose the previous one, but there'll be even less error in this estimate of the mean here. So what we've seen is that if we take a sample from a normal distribution and we repeat it, we're going to end up with another normal distribution of the means. So this is the sampling distribution for the means. And then if we want to make statements about this estimate of the mean, which is what we'll do next week when we start looking at calculating standard errors and confidence intervals, we can use the fact that we know it would be normal if we did it a lot of times to make a confidence interval, and we use these ideas later for testing. However, we started with a normal distribution. So the question is, what happens if we don't start with a normal distribution? What if it's skewed when we start? What will happen to the distribution of means then? So let's set this back to 5 and let's draw ourselves a skewed distribution. So let's say it's actually a bit faster to walk across campus. What have I got? About 13 minutes there. But for some people, it still takes half an hour to get from one side to the other. So if we draw a sample this time, that's just one sample. We'll take another. This is going to be quite slow. Let's do 10,000. And it is looking a little bit skewed. So the distribution of means when we have a small sample size from a skewed distribution is also looking a little bit skewed. So we wouldn't want to assume that this is perfectly normal. It's actually not that bad, to be fair. But this distribution is also not that extreme. We can't draw a crazy extreme distribution just because we're limited by the axes, but I'm sure you could draw something more extreme than this. And even if we do loads and loads of samples, this is kind of where it has settled down. This is with a sample size of 5. What if we took a larger sample size from our distribution? So let's go back up to 25. I can't remember what we used last time. Let's go 25. Clear the lower 3 in case it was remembering any information in the background. Maybe I shouldn't have animated that one. It's going to take a long time with 25. But we can see our people walking across campus. Some of them do it quickly. Some of them take a while. This person's super fast. All right, 10,000 at once. Another 10,000, 100,000. This is actually looking almost normal. So even though the original distribution was skewed, once we start just sampling the mean and just looking at what happens to the means of each of those samples, they become normal. And this is the central limit theorem that says even if your original distribution is not normal, if your sample size is big enough, the sampling distribution for the mean, or the distribution of means on repeated sampling, will be approximately normal. It doesn't mean that the distribution of means will be approximately normal for absolutely any parent population. You have to have a big enough sample, and the parent population can't be crazy extreme. So what I would like you to try and do, see if you can find a distribution which is extreme enough that when you do repeated sampling, even with n equals 25, the central limit theorem would not apply. How can you break it? How extreme does this need to be to break it in this case? Now, just because the central limit theorem may not apply at n equals 25, we can't actually go any higher than this. It might be that if you have a sample size of 100, the distribution of means does start to look normal. So this is just at one particular point. And this is where sometimes you'll get a sort of random advice to say that you just need a sample size of around 30 is usually the rule of thumb I hear, which is kind of true if the only thing you want to do is estimate a mean and you're not doing anything else with your data, and it's not crazy extreme. A sample size of 30 should be enough to estimate the mean and assume a normal distribution here. However, that's a very limited situation, and there's plenty of cases where you actually want to do more than just estimate a single mean, and so you might need a larger sample size. The sample size will really depend on what it is that you're trying to find out, the variation in your data, how complex your modelling is, how many variables do you have, and sometimes it's just limited by practicality. What resources do you have available to you? So there's lots of things that can affect what sample size you end up with in any particular study. So have a go at trying to find an extreme population where the distribution of means is not normal, and we will be talking more about the normal distribution, the central limit theorem, and how we put confidence intervals on our estimate of the mean in the coming weeks.